Um, as if we have let's do the two-dimensional, think about two-dimensional curve here. As a particle, let's say, moves along the curve there, the unit tangent vector turns as well. So if I go from this point to this point to this point, and think about the unit tangent vector, which is 1 unit long, but that unit tangent vector turns along the curve as well. However, since it's the unit tangent vector, only the direction is changing because the magnitude of a unit tangent vector is 1 unit long, right? Well, the rate at which that unit tangent vector changes, that's called the curvature kappa. Greek letter kappa. Okay, it looks like the kappa is the official title, Greek letter kappa. So it's the rate at which the unit tangent vector is changing, at which the direction of the unit tangent vector is changing. Okay, well, how does that translate into formula? Well, so the rate at which the direction is changing, that is a derivative. So it's the derivative of the unit tangent vector, and it's with respect to s. And we want the magnitude of that to give us a number. We don't want a vector out of that. We want the magnitude of that vector. So kind of gets back to some of the things we've talked about before, rate of change of something. So if the curvature is how the direction of the unit tangent vector is changing, the rate at which it changes. So and this is one kind of application, I guess you might say, of using the arc length, well, initially there. That's by definition what curvature is. And we'll do an example, maybe kind of get a feel for it. But now, if, I guess in practice, it's easier to do this in terms of not S, but in terms of T. We don't want to have to change it over to necessarily S's. So here's what kappa is, and so if we write this in terms of T, here's what it is. It's d t vector divided with respect to T over ds t. So it's the magnitude of the tangent vector derivative. That's what that is. And this is the derivative of S with respect to T. That is, we didn't point that out in my previous. Here's what this can be. All right, so we know that S of T equals the integral from A to T and so if we take the derivative of this with respect to T, it's by fundamental theorem of calculus. It turns out this is just the magnitude of that RT vector, derivative vector. That's what this is. It's from fundamental theorem of calculus. That's probably the easier way to calculate kappa. Tangent vector is derivative, magnitude divided by r prime derivative of the r vector. Easiest way to find kappa. Yeah, so here's a good example. Find the curvature of a circle, radius A, which in vector valued function form is A cosine t I plus A sine t j. That's what a circle looks like. Vector form, two-dimensional circle. That'd be a circle of radius A. All right, so we're going to calculate this curvature. So to find it, we have to find, well, of course we need the derivative. A is just a number, so it'd be negative A sine t j I plus A cosine tj, just the derivative of those two things. All right, now, this is the derivative of the tangent vector, so you have to find the unit tangent vector, and then this is going to rely upon its derivative. So the unit tangent vector, remember the way we get that is you take r prime of t, but we want to unitize it, so you divide that by its magnitude. So yeah, we take that negative A sine t I plus A cosine tj, but divided by the magnitude, which would be square root of those squared, so it'd be A squared sine squared plus A squared cosine squared. Because that's going to work out pretty nicely. Factor off the A squared, sine squared plus cosine squared, square root of A squared. That's just going to be A, yeah? Which works out nicely. That's just negative sine ti plus cosine tj, because the a's just cancel out. So that's our unit tangent vector. All right, so we're almost there. We've got this one. We just need the magnitude of that one. So t prime here, what's t prime? Well, it'll just be negative cosine ti minus sine tj would be that vector. So kappa is the magnitude of that divided by the magnitude of the r prime. So what does that work out? Magnitude of that would be square root of cosine squared plus sine squared, that's just going to be 1. Divided by the magnitude of this one, which is, we just did that, it's A, right? we got 1 over A. So depending on the size of the circle, the curvature is 1 over A. Now remember what that means. The curvature is the rate at which the unit tangent vector is changing direction. So this makes sense because if I have a small little circle, the unit tangent vector is changing pretty quickly if I go around. However, if I have a bigger circle, and say I'm going the same increments there, the rate at which the change, so this one in four little increments, we've already changed from this direction over to this direction, right? So it's changing pretty quickly. However, the same increments here, 4 equally kind of spaced around there, the direction of the unit tangent vector has not changed very much. So you see, so that makes sense. If you have small A's, so like A is a half, A is a third, that's going to give you 1 divided by a third or 1 divided by a half. That's 2, 1 divided by a third. So the smaller your, so kappa is 2 there, kappa is 3. The smaller the radius, the larger the curvature, the more it's changing. But the larger, like if I have A is 10, the curvature kappa is 1 over 10. It's a small curvature. So you see, you can kind of get kind of a feel for what this means. It's the rate at which the curvature is changing. It changes for small circles, it changes faster. For larger circles, the curvature doesn't change very much, so smaller curvature. Anyway, just to give you an idea. All right, now, one other thing here to talk about is the unit normal vector. One thing they go through this in the book, but if a vector has a constant magnitude, so it's equal to a constant. And one example is the unit tangent vector. It has a constant magnitude, it's 1. Then the vector and its derivative vector are orthogonal. And it doesn't have to be the unit tangent vector, that's just an example. Like spelling. Orthogonal. Which, you know, that's, for vectors, that's the perpendicular word, right? Word for perpendicular. So vector and its derivative vector are orthogonal. So if I've got this vector and its constant magnitude, so call it R, whatever. If I do its derivative vector, it's orthogonal to that. So it's going to be 90 degrees. The angle between those vectors is 90 degrees. They're orthogonal, which may not be my best 90-degree angle drawn there ever, but yeah, those. That's, like I said, that's shown in the book, and we're going to use that, in fact, here for this unit normal vector. Because, remember when we were talking about tangents, and slopes of tangents and all that, we also talked about tangent lines. We also talked about normal lines. And the normal lines, like here, if we have a tangent line, T, then the normal line is the line that's 90 degrees to that. That's the normal line. Well, same with unit normal vectors. The unit normal vector is going to be the vector that's orthogonal to the unit tangent vector. And it's going to play off of the fact that I just gave you there. So the unit normal vector is this, n of t all right, so what we just said was, so yeah, if we've got t here, whatever direction it's taken on there, then we know that we've got another vector orthogonal to that with its derivative. The only thing missing there is I want it to be a unit normal vector. So I know that this is orthogonal to it, to be normal. I want it to be a unit normal vector, so what do I have to do there? To make it unitized. Divided by its magnitude, right? So the unit normal vector is the vector orthogonal to the unit tangent vector, 1 unit long. That's 1 unit long. So we've got, again, with the two-dimensional versions here, much easier for us to draw. All right, so we've got this t value. We've got this unit tangent vector. The unit normal vector is 1 unit long, and it's orthogonal to the unit tangent vector. Just like the normal line was 90 degrees from the unit tangent, just the tangent line. Okay. So let's find unit tangent vector and unit normal vector for this. R of t equals our old friend cosine t I plus sine t j plus t k. We've used that one quite a lot, but I don't think yet we've found the unit tangent vector for it. So the unit tangent vector, well, the way you find it is you take the derivative vector divided by its magnitude. So the derivative vector here, we've done that quite a bit. Negative sine of t I plus cosine t j plus 1k. Divide that by its magnitude, which would be sine squared t plus cosine squared t plus 1 squared So that's going to work out to be negative sine ti plus cosine tj plus 1k, or just k, divided by the square root of 2. How are we going to write that? You could write it that way, you could write it negative sine t divided by the square root of 2. I don't know how to write it, but we could write it this way too. Right? You know the way to write it. That's the unit tangent vector. Unit normal vector, well, it's similar there. Take the unit tangent vector, do its derivative, and then divide it by its magnitude. So d prime, what is it? Negative 1 over square root of 2 cosine t I plus 1 over square root of 2 times negative cosine t j plus, plus 0, right? Do the derivative. Derivative, yeah, k component is 0 because it's a constant. Then divide that by the magnitude of that, so we have the negative 1 over square root of 2 cosine t squared plus 1 negative 1 over square root of 2 sine of t squared, and then the 0 squared. See how that cleans up. What does that be? 1/2 cosine squared plus 1/2 sine squared. So that's just going to be the square root of 1/2. So hey, look at that. Aren't these all going to, so if I divide, isn't that 1 over square root of 2? So we'll have negative 1 over square root of 2 divided by 1 over square root of 2. That's just going to be negative cosine t I minus sine tj. I guess I do need this, okay? That'd be empty. And then you can evaluate those wherever you want, t equals 0. So yeah, remember this is the helix, so this would give us the unit tangent vector at a particular value, and that would give us the unit normal vector, so it should be orthogonal to that. All right, any questions or concerns?